And this tutorial will be on combustion, and it will be done in several parts. This is the part 1. In this tutorial we will discuss about the fuels and its analysis, calculation of GCV and NCV, calculations of minimum theoretical air, calculations of various gas compositions. Then we will discuss about the 3 T's of combustion and their significance on combustion. And finally, we will discuss about the combustion optimization. So let's start with fuel here. Now, the fuel which we are using in boiler are basically called fossil fuel. Fossil fuel is the fuel which is produced over a long period of time. Billions of years ago, the earth crust was filled with a dense forest. Now when this forest dies, it goes down, forms a pit first, and then because of the lots of upheaval which used to be there during the early stage of the earth, this crust went down below and below, and after a lot of compression, because of the lot of pressure on it, and due to the anaerobic condition, because there is no oxygen there, and because of the vicinity to the core, the temperature is also high. It has gone through a transformation. Some part we get as the upper part we get as the lignite, then we get the bituminous and subbituminous coal, the one which we use in our boiler. So since at one point of time these were living beings, plants, animals, it has to be hydrocarbon. Therefore, the two major ingredients in any fossil fuel which you are going to find would be carbon and hydrogen. Along with carbon and hydrogen in some fuel, we also have sulfur. Now, these 3 ingredients of a fuel are of interest to us. Why? Because the carbon, hydrogen, sulfur, when in presence of oxygen it reacts. The oxidation is a highly exothermic reaction and it gives a lot of heat. So that is the purpose of these 3 ingredients. Now if we talk about the types of fuel, there will be solid fuel. Commonly you can say, apart from the coal which we use, in quite a number of plants you are using bagasse. The sugar plants are using bagasse. Then you'll be having pet coke nowadays used at various boilers, and lignite would be also there. There would be other solid fuel like rice husk and the biomass fuel. Now it is used in quite a number of boilers, but most commonly these are the fuel. In solid fuel, these are the fuel which are being used. In liquid fuel, the most common fuel is FO, naturally furnace oil. Apart from that, LDO, LSHS, then there used to be naphtha. Nowadays it has become very costly. Earlier, naphtha was used in a number of plants. And in gaseous fuel, there will be primarily natural gas. Of course, there are refinery fuel class, RFG, used in most of the refineries as a boiler fuel. Then in a steel plant you will find the blast furnace gas, BFG, and coke oven gas, COG, etc. But most common gaseous fuel will be natural gas. Now see, when the ingredients are important, so first thing we need to understand is the ingredients available in the fuel. So we analyze the fuel. So first we talk about the fuel analysis. Now when we talk about the solid fuel, there are 2 types of analysis available for solid fuel. The most common one, which is done almost in every power plant, is the proximate analysis. In a proximate analysis, what you get is the moisture. Of course, it's a combination of surface moisture and total moisture, inert moisture. And then there will be volatile matter, the fixed carbon, and ash. Now, percentage analysis of these components of the fuel are very important because this has got a lot of significance on the combustion. But the one analysis which is going to give us the actual ingredients of the fuel is the ultimate analysis, which is done for all types of fuel. In ultimate analysis, you get the elemental analysis like carbon, hydrogen, sulfur, everything would be available in the ultimate analysis. Of course, the ultimate analysis will be available to you. Suppose in a BOE examination, it will be a percentage, mass percentage for solid and liquid fuel, and it will be volumetric percentage for a gaseous fuel. Now, whenever you get a ultimate analysis, the first thing you do is you total it, and the total should come to 100. And if it is not coming 100, that means it is short by whatever percentage, then the first thing you should write is assuming the unaccountable part as non-combustible. You must not forget to write that on your answer sheet, right? Assuming the unaccountable part as non-combustible. The next thing you do is convert the percentage analysis into fraction analysis, that is mass fraction, right? So you divide it by 100, and then what you get is the kg per kg of fuel. Once you have written this, assuming the unaccountable part as non-combustible, you don't have to worry about rounding off this to 100. Whatever is there, you just get the fraction analysis. Okay, and you don't need to change the ash, because we will, in our combustion calculation, we don't need actually ash percentage. Okay, now if we go back to the proximate analysis, the one which you get is the moisture, the volatile matter. Now all of them are having some significance in combustion. So let us first talk about the volatile matter. Now what volatile matter is, basically gaseous hydrocarbons entrapped inside the solid fuel, right? So whenever it is exposed in the furnace temperature, high temperature, immediately the gaseous part comes out, right? That's why it's called volatile. And these are the part which first take, it participate in the combustion, right? Because this is gaseous, and with air it will create a homogeneous combustion mixture. So naturally, it will be burned faster. So if I talk about the advantages of, or rather the significance of this volatile matter, if the volatile matter is in a higher percentage, this particular fuel will be easy to burn, right? So the greater will be the combustion speed. We will call this fuel more reactive type of fuel. Less the VM percentage, it is non-reactive fuel. For example, your pet coke, which is having a very little volatile matter, is a highly non-reactive type of fuel, and it's very difficult to burn actually. But the other aspect is, see, in fuel, the flame is actually contributed by the volatile matter. If you see the charcoal, right, what charcoal is, after you remove the moisture and the volatile matter from the coal, what remains is charcoal. Now if you burn a charcoal, suppose in a tandoor or somewhere, if you notice, you will not see any flame, right? Why? Because the flame is actually contributed by the volatile matter which is missing in the charcoal. So higher would be the volatile matter, the longer would be the flame length naturally. And you can imagine in a furnace, if we are not in a position, or we are not able to give the oxygen in the right area, and this is taking longer time to burn, right? This flame length being longer, it may reach to the upper part of the furnace, which will lead to something what you call delayed combustion. So that can be a problem if you are having a higher percentage of VM. One more problem with VM is that if we are having higher percentage of VM, it is going to increase the chance of spontaneous combustion in the storage, right? So you have to take care of this spontaneous combustion by sprinkling water to make it moist, so that it doesn't slip easily, and because of the friction, it will not generate the spark, and the spontaneous combustion can be restricted. That's why the water is sprinkled over the coal, or in a coal yard. You might be seeing that. Again, if you are having a higher percentage of VM, you have another limitation, and that limitation will come in the mill outlet temperature set point in a pulverized coal-fired boiler. In a pulverized coal-fired boiler, the mill outlet temperature set point is actually controlling the what you call is the CAD, cold air damper opening, right? And in order to limit this temperature to a lower temperature, there will be more opening of the cold air damper, bypassing the air preheater. As a result, the gas temperature, exit gas temperature will increase, right? So that can be another problem with high percentage of VM. So it is not all good things about having a high VM being a reactive type of fuel. It will have some disadvantages also. Now talking about the ash, what is ash is basically is the mineral matter which has along with the plants and other things, it was also there when the coal was formed, right? And this mineral water will not take part in the combustion. So after the combustion, this will remain as ash. Again, ash will have various problems. Most of the things, if you talk about ash, would be problems. Advantages are very little. Only advantage you can think about in a FBC boiler where ash is also, used as a bed content, or rather the bed mass is increased by the ash, and the heat transfer and everything is affected on by that. But otherwise, ash has got all sorts of problems. The major problem, or rather the most critical problem with ash, which is true for all solid-fired boiler, is the erosion, right? Flue gas erosion is primarily caused by fly ash. The ash which comes with the coal or any fuel, 10-20% of this ash will remain in the bottom, right, which is called bottom ash, and about 90 to 80% of this ash goes with the flue gas, which is called fly ash. And this fly ash, high velocity fly ash, will cause a lot of erosion. Other problem is, of course, if the ash melts, right, then first of all it can cause slagging. What is slagging? Slagging is nothing but molten ash getting coated over the surface of the tube, right? So heat transfer will be affected, number one. This slagging, if it goes on taking place there, it can go on accumulating and it can actually lead to fouling. That is, the flue gas flow will be restricted, the ID current will increase, and all sorts of problem might come. And this slagging, when it accumulates and then it gets solidified because of cold air coming to this, it forms a very hard, glassy type of solid formation, which is called clinker. Now, clinker is one of the major problem in FBC boiler also. When we talk about the FBC technology, we'll see. That's why we have to be very, very careful about the bed temperature control, and always take this ash fusion temperature into consideration. And then there can be another problem with the ash is sometimes in case of slagging, in certain conditions with high sulfur and contaminations like vanadium, sodium pentoxide, it might cause high temperature ash corrosion, right? So that is another. In fact, this corrosion is not very common, but we are still going to discuss it when we discuss about the corrosion and failure issues. Okay, let us come back to the combustion now. First, let us see the combustion mechanism. When fuel burns in presence of air, we know that the chemical reaction will be taking place is the oxidation of the carbon, hydrogen and sulfur, and these are highly exothermic reactions. So if I take a look at this reaction, the carbon will react with oxygen to form CO2 and it will produce 8084 kilocalorie of heat per kg of carbon. That means 1 kg carbon reacts with oxygen, forms CO2. 8084 kilocalorie will be the heat released by this combustion reaction. We would rather, if we are from Gujarat, we would rather follow the heat value of carbon, hydrogen and sulfur in kilojoule. They are actually not exactly matching in terms of conversion factor of kilocalorie to kilojoule is we know 4.187. But if you multiply 8084 with 4.187, you will not actually get 33,800 kilojoule. Whatever, you need to remember these three heat values of carbon, hydrogen and sulfur. Hydrogen will react with oxygen to form H2O, and the heat value will be 1,44,000 kilojoule per kg of hydrogen, 34,500 kilocalorie. Sulfur will react with oxygen to form SO2, and there will be 2224 kilocalorie heat released. In kilojoule it will be 9,300 kilojoule. The problem is that carbon, when reacts with oxygen, will not form CO2 in the first place, right? That is the major problem of combustion. If you see the reaction of carbon, carbon reacts with oxygen to form CO first, and a part of the heat is released, which is 10130 kilojoule. The remaining heat will be released when we further oxidize the CO, and the formation of CO2 will take place. That's why we call this part as incomplete combustion, and the CO2 formation is called complete combustion, because that is going to give us the total heat value of carbon. In fact, when we talk about the combustion, the 3 T's of combustion and other things, and the combustion optimization, we'll discuss about this part further. But so far as BOE calculation is concerned, we do not consider incomplete combustion unless it is being told, right? Specifically being told. So if there is a fuel and there is a carbon, the combustion result will be CO2. That is what we are going to consider, right? So if I want to calculate the calorific value first, calorific value can be theoretically calculated. It can also be measured by bomb calorimeter. There is an instrument called bomb calorimeter. Now, calculation of calorific value, if we see, the first thing is that what is calorific value is, it is the heat released by complete combustion, as I told you earlier, complete combustion of 1 kg of fuel in case of solid and liquid fuel, or 1 nm cube or sm cube of fuel in case of gaseous fuel. Again, this calorific value are basically two types. One is the GCV, gross calorific value. The other is the NCV, the net calorific value. So now we are going to see how to calculate the GCV and NCV. But for this calculation, what you need is the ultimate analysis of the fuel, right? Then you can theoretically calculate the GCV and NCV. So suppose we have an ultimate analysis of the fuel. The gross calorific value is basically the total heat value. That means all the combustible components of the fuel is reacting with oxygen in complete combustion reaction, and the total heat that is released, right, even including the heat that is actually being taken away by the water which is forming steam, right, including that heat will be the gross calorific value. So no deduction, total heat released by that. So for example, if we take a look at the ultimate analysis of a fuel, say carbon, hydrogen, sulfur is given as C, H, S, like that. Now in this, if you see, the carbon, hydrogen and sulfur will be the three components which will be giving us heat. The carbon will give us at the rate of 33,000 kilojoule per kg. We have got C kg. So 1 kg of fuel burns. That means C kg of fuel will react. In complete combustion, it will give us 33,800 C, and like that. But here, please remember one thing. If there is oxygen mentioned in an ultimate analysis, let us say here it is mentioned O kg, then there will be a deduction from the hydrogen. Why? Because this oxygen has come from, we do it from the back calculation. So it has come from the analysis of H2O, which is forming after the combustion reaction, right? And some amount of oxygen is coming from the H2O, and if oxygen is coming, some amount of hydrogen is also coming from H2O, and that is not present in the fuel as hydrogen and will not give us the heat, right? So if there is O kg hydrogen, there will be a deduction of O minus 8 kg from the hydrogen. Why the deduction is O by 8 kg, I'll explain later on, but that is going to be the deduction. So if 1 kg of this fuel burns, then carbon will give us 33,800, hydrogen will give us 1,44,000 into H minus O by 8 as we have deducted, and the sulfur will give us 9,300 S, because S kg of sulfur was there. Now this is the formula for GCV. It is not going to be a bad idea to write this formula and remember this formula as a theoretical calculation of GCV. You can of course mention when you are using this formula that assuming the heat value of carbon, hydrogen and sulfur as 33,800, 1,44,000 and 9,300 respectively, right? Okay, now while calculating the NCV, we have to calculate it from the GCV, right? And okay, let me first explain why O by 8, right? I have not explained that, so let me first explain why O by 8. For that, you take a look at the molar reaction. Now when we talk about the hydrogen reaction, 2H2 plus O2 is 2H2. What does it mean? That hydrogen 2 molecule reacts with oxygen 1 molecule and forms 2 molecule of H2. If you remember the mole kilomole concept, we have seen that mole kilomole is nothing but a particular number of molecules. So 2 kilomole of hydrogen will naturally react with 1 kilomole of oxygen, and the formation will be 2 kilomole of H2 moisture. Now if you remember the kilomole concept, you will also remember that 1 kilomole is having a mass which is equal to its molecular weight in kg. So if it is hydrogen, 1 kilomole will be 2 kg, so 2 kilomole will be 4 kgs, and oxygen 1 kilomole is 32, so it will be 32 kg for oxygen, 4 kg for hydrogen. So now we have a mass reaction. 4 kgs of hydrogen is reacting with 32 kgs of oxygen to form 36 kg mass balance of moisture. So divide the whole thing by 4, we know that 1 kg of hydrogen will react with 8 kgs of oxygen. Or the reverse, if we see, 1 kg of oxygen will react with 1 by 8 kg of hydrogen, right? So if I am having O kg of oxygen, it will react with O by 8 kg of hydrogen. Therefore, if I had O kg of oxygen in the fuel analysis, I will be deducting O by 8 from the hydrogen for calculation of GC. I hope I could explain the O by 8 part. Okay, now take a look at the NCV calculation. Now, what is NCV? NCV is when you deduct the heat that is taken away by the moisture. Now there are two parts of moisture. One is the moisture which is already available in the fuel. The other part which is coming from the combustion of hydrogen. Now this two moisture will take some amount of latent heat. That latent heat will not be available to us, right? So from GCV, when we deduct this latent heat, then what we get is the net calorific value, which is the available heat basically from a fuel. Now if we consider the partial pressure of moisture as compared to the amount of moisture available in the furnace condition, and at that partial pressure, the formation temperature of the vapor will be somewhere near 15 to 20 degree. So in theoretical calculation, we take the 15 degree as the formation temperature, and whatever the latent heat corresponding to this 15 degree, we deduct, which will be taken away by the moisture which is formed by the combustion of this fuel. So first, if I am having the same analysis, then 8 kg of hydrogen is going to give us 9 kg of moisture, which you have just seen. And if m kg moisture is already there, then the total moisture will be 9H plus m. So from the GCV, if I deduct this 9H plus m, taking away 2466 kilojoule, which is the latent heat at 15 degrees centigrade, so whatever remains is the net calorific value. So that is how we calculate the theoretical net calorific or lower calorific value. GCV minus 9H plus M into 2466. If the fuel doesn't have moisture, we don't use M, only 9H into 2466 and like that. So let us first deal this with a particular problem. The problem says the fuel sample has 86% carbon and 12% hydrogen by weight. Calculate the higher, that is GCV, and the lower calorific value, that is NCV, of the fuel using the fundamental chemical equation. Now, as I told you, in a percentage analysis, first I total it, right? And I see whether it is coming to 100 or not. In this case, it is not coming to 100. There will be some 2% which is unaccountable, right? So in our answer sheet, the first thing which we are going to write is assuming 2% as non-combustible, right? So after that we see the fraction analysis. So we have here carbon as 0.86 kg and hydrogen as 0.12 kg per kg of fuel. So 1 kg of fuel after combustion, after complete combustion, what we are going to get is 33,800 kg per kg of carbon. So 0.86 into 33,800 plus 1,44,000 into 0.12. Here there is no deduction of O by 8 because there is no oxygen in the fuel, right? So 46 till 48 kilojoule per kg is going to be the gross calorific value. Now net calorific value, again we deduct the moisture part. So it is 46,348 minus 9 times the hydrogen 0.12 into 2466. There is no moisture available, so not 9H plus M, only 9H. And the net calorific value will be 43,684.72. Now this was a simple analysis given. If we take an actual analysis of a fuel, for example, there is a typical analysis of a Indian coal, right? With all carbon, hydrogen, sulfur, everything is given. So if I take this actual analysis, if I need to find out the GCV and NCV, as I told you, the first thing I do is I total it, right? Add it up and see whether it is coming to 100% or not. In this particular analysis, it is actually coming to 100%, so there is no problem. The next thing what I do is I convert this to the fraction analysis in kg per kg and then use the GCV formula. The GCV will be 30,800 into C plus 1,44,000 into 8H minus O by 8, that is 0.0989 by 8 plus 9,300 into S, that is sulfur 0.0041. I get the GCV as 16127.51 kilojoule per kg, right? When I want to find out the NCV, it will be GCV minus the moisture formed by hydrogen 9H plus the moisture already available in the fuel, which will take away 2466 kilojoule heat, right? So NCV comes to 14537.49. Again, not very difficult to find out. Only thing is you have to remember the heat values of carbon, hydrogen and sulfur. Now talking about the gaseous fuel calorific value, right? Now this will be a little different than solid and liquid fuel. First of all, the unit will be different. It will be kilojoule per nm cube or sm cube instead of kilojoule per kg. And the ultimate analysis which will be available for the gas would be a little different, right? It will not be having the carbon, hydrogen, sulfur analysis. On the other hand, if I take a look at the typical natural gas analysis, it will give us the various hydrocarbons CH4, C2H6, C3H8, like that, right? Now this percentage analysis here will be first of all mole fraction or volumetric percent, right? That means 1 nm cube of this fuel will have 0.939 nm cube of CH4, like that. And another thing, all these individual hydrocarbons CH4, C2H6, C3H8, they are all having different heat values, right? So in BOE, if you need to find out the calorific value of a gaseous fuel, the first thing you need is the heat value of all these gases, right? So don't worry, it will be given. If they want you to find out the gaseous fuel calorific value, they will give you. For example, let us say the problem like this. This has come in one of the BOE examination. Find out the lower calorific value and the higher calorific value of the following gaseous fuel. Volumetric composition is CH4 69%, C2 is 629%, and N2 2%. So if I total it, it comes to 100%. So no problem. Now HCV of the gases is given, right? CH4 is given as 39,000 kilojoule per nm cube. C2H6 is given as 71,500 kilojoule per nm cube. So again, the fraction analysis will give me 1 nm cube of this fuel will have 0.69 nm cube CH4 and 0.29 nm cube C2H6. Now, if 1 nm cube this fuel burns, 0.69 nm cube CH4 burns, and 1 nm cube CH4 gives you 39,000 kilojoule. So GCV calculation will be very easy. 39,000 into 0.69 plus 71,500 into 0.29. That is 47,645 kilojoule per nm cube. Now, when I want to find out the NCV in a gaseous fuel, that is a little bit tricky, but not very difficult. Once you found out the GCV, see earlier what we have done in case of solid and liquid fuel, we found out GCV, then we found out the mass of moisture formed after complete combustion of 1 kg of this fuel, right? The mass of moisture formed in kg. Why? Because it is taking away the heat in kilojoule per kg, so we need to find out the mass of moisture. So in case of gaseous fuel also, we need to find out the mass of moisture formed after the complete combustion of 1 nm cube of this fuel, right? In kg, we need to find out the mass of moisture resulting from the combustion of 1 nm cube of this fuel. So the first thing we need to know now in case of gaseous fuel, earlier what in case of solid and liquid fuel we have done it the mole to mass conversion, right? Mole reaction to mass reaction. In gaseous fuel, what we need is a conversion of mole reaction to volumetric reaction. The first thing what we do is we write down the reactions. In this case, the CH4 is going to react with O2 and form CO2 and H2O. We have to balance it. C2H6 will react with 3.5 O2 and 2 CO2 and 3 H2O will be formed. Now, if we take a look at this molar to volumetric reaction, in case of CH4, we see 1 kilomole of CH4 is going to react with 2 kilomole of O2. Now, if I talk about nm cube, that is enthalpy condition, and we have seen in gas laws that when temperature and pressure is same, the volume is proportional to the number of molecules. So, if 1 kilomole is reacting with 2 kilomole, then 1 nm cube will react with 2 nm cube and vice versa, right? So that is how we calculate the reaction. 1 nm cube is reacting with 2 nm cube and the formation of water is 2 nm cube from this reaction per nm cube of CH4. In case of C2H6, it is 3.5 O2 will be reacting with 1 nm cube, right? So 1 kilomole is reacting with 3.5 kilomole and 1 nm cube will react with 3.5 nm cube. The formation will be 3 nm cube of H2O from 1 nm cube of C2H6. In our fuel, CH4 is 0.69 nm cube. So 1 nm cube is forming 2 nm cube of water. 0.69 nm cube will form 1.38 nm cube of water, and 0.29 nm cube of C2H6 will form 3 into 0.29, that is 0.87 nm cube of water. So after the complete combustion of 1 nm cube of this particular fuel, the total water will be 1.38 plus 0.87, that is 2.25 nm cube per nm cube of fuel. But that doesn't solve our problem. We need the mass of water. So what we do, again we remember the gas laws. At enthalpy condition, the density of any gas is what? It is molar mass by 22.4 kg per meter cube. So in case of H2O, the molar mass is coming to 18. So the density would be 18 by 22.4 kg per meter cube at NTP. So 22.25 nm cube can be easily converted into 1.808 kg of water resulting from 1 nm cube of this fuel combustion, right? So now we have found out the mass of the moisture form. Now this moisture is going to take away at the rate of 2466 kilojoule heat from the GCV. So NCV calculation will be GCV minus 1.808 into 2466, that is 43186.47 kilojoule of energy. Now in this particular tutorial I would conclude here. I would deal with in the next tutorial, next part of this tutorial, I will deal with first the air calculations, the theoretical minimum air calculations. Then I will be dealing with the gas composition calculations, right? And possibly in part 3, we'll be dealing with the 3 T's and its significance in combustion and how to optimize combustion, right? Till then what you should do is, you should practice with the examples that is given in the study material, in the chapters of combustion, right? And do all the GCV and NCV calculation problem that you find there, right? Till then, thank you very much. Goodbye.